Okay, my babes. We are going to go over the quiz problems from Dr. Curly's quiz because that's what's up. Number 1 is a mechanism problem. And it starts off like this. If you did not watch my last video on mechanisms, I highly recommend before looking at this one because this one is scary. So, every single problem starts the exact same way. I'm gonna go a little bit faster on this one because I've already taught this content. It's just a little bit different than before. So we have the exact same thing, except now this is a wedge, but it doesn't matter. Our oxygen has 1 lone pair, 2 hydrogens. Our bromine is out here looking all cute by herself. And our oxygen has a positive charge. We redraw this molecule after having breaking off water. I don't have to draw water because it's not necessary. We still have this. We have our carbocation. Now, we need to evaluate if we add something to our carbocation, will it make a stereocenter? 2, is our carbocation secondary or tertiary? Okay, great. Number 1, will this make a stereocenter? If we add bromine right now, will it? Maybe. Let's check. We've got a hydrogen hiding right here. She's so cute. And we got a methyl. And then we have all this. So if I had a bromine here, yes, it would make a stereocenter. However, we need to answer number 2. This carbocation is secondary because it has 1 hydrogen substituent and 2 non-hydrogen substituents. So it is a number 2 carbocation. We don't like this because tertiary carbocations are more stable than secondary carbocations because of all the things. And at this point, we need to say, okay, wait, is there another carbon in this chain that's available for me to steal from to satisfy this carbocation and instead make a tertiary carbocation? So we're looking. No. Yes. How exciting. We know that we're going to choose this one instead of these because this carbon has 3 non-hydrogen substituents. So it's already, we know that if we take something away from it, then it can have the tertiary carbocation status. So what do we take from this carbon? Well, we want it to be a tertiary carbocation, so we can't take the methyl group because if we took the methyl group, then it would just be secondary and be in the exact same position as we started in, and that's not productive. So what if we take this hydrogen, right? What if we put this hydrogen right here? How will that change our carbocation, and how will that change our questions? So first, if we had a hydrogen here, will it make a stereocenter? And the answer is no, because this carbon already has a hydrogen substituent. If I had a second one, then it can't be a stereocenter because of all the rules. So no, it won't be a stereocenter anymore, which creates less work for us. And then what are we left with? This will be satisfied. This carbon will have 4 substituents, and this carbon will be a tertiary carbocation because it will still have 1, 2, 3 non-hydrogen substituents. So that's what we're going to do because that is the best option. And then I've got this. This is planar now because we want to represent our carbocations as planar. And now this carbocation is no longer a carbocation because we satisfied it. We just don't show hydrogens in chain structures, so that's why they're hiding and they're looking all cute. Sorry, that's a hydrogen. Okay, now reevaluate our questions. We already know it's tertiary, said that a million times. If I add bromine here, will it make a stereocenter? Yes, because this is a methyl group, this is an ethyl group, and then this is a pro something group. And that means that we have to draw 2 different products because they're going to be stereoisomers. So first we have this one where our bromine could be a dash and our methyl group could be a wedge, or our bromine could be a wedge and our methyl group could be a dash. And I know that this is true because just like good twin, bad twin, maybe this is our good twin, maybe this is our bad twin, or the other way around. But I know that both of them are present in a solution. And that's the important thing to keep in mind. So that was the first problem. And now we're going to do the second problem. A second to erase. At this point, you could probably skip, I don't know, 10, 20 seconds ahead because I got to write down the next problem. So number 2 is comparing 2 different molecules and asking what kind of isomers they are, if they're isomers at all. And at this point in our OChem career, we're just going to assume that it's an isomer because it would be silly for them not to be isomers. So we've got this, and then this little thing right here just means that this is a carbon and this is another carbon. But to help my brain function, I draw out this carbon and this one, just because, you know, that's my brain, whatever it's doing up there. If that confuses you more, then don't pay attention to it, but that's just how it's gonna happen. And then we have our OH, H, and then ethyl group, H, carbon, carbon, CH3. Okay, so now you're like, what the hell? Another one of these, right? Right. So the best way to start this problem is to pick on a substituent and say, okay, I'm gonna look at you and then compare you to the other one, another molecule, and make them match up. It's very cost effective with your time. Because if you're trying to worry about too many things at once, then you're just gonna go into overload and cry. So here's my little handy dandy wedge dash structure with 2 carbons on it. And you have to decide which molecule you want to manipulate. I'm going to choose the right one because I said so. If you do the left one, you'll get the same answer. And if you don't get the same answer, you did something wrong. So we're going to do the right molecule because why not? And I'm going to pick on this OH substituent. Right off the bat, we know that this OH is on the front carbon and this OH is on the back carbon. So we have to flip our molecule like this to make the back carbon become the front carbon, and vice versa. So I'm going to orient it so it makes sense in my brain. Make sure that it's actually represented as being staggered. Also important. If I look down it like this, I can see that it is staggered, which means I'm starting in the right spot. Here's my OH right here. Love her. When you make a pancake flip of a molecule, the planar one is going to stay in the same spot because it's just going to stay planar. If this is in the plane right now and I turn it, it's still going to be planar. The only thing that changes is the front and the back. So I know that over here, my OH is still going to be an OH. I know that my CH2 and CH3 will switch because whatever is in the front, this hydrogen, is going to go in the back, and then whatever's in the back is going to go in the front, like that. So it's a short version. Look at my other video for a longer version, and thus, when our CH3 is going to be like this, we know that our H is going to be out, and our C double bonded to C is going to be in. Now, they're still not matching. Shit. What are we going to do? We are going to turn the molecule to make my OH group now be a wedge instead of plane. And that just means that I'm going to turn it like this. Okay? If I turn it like this, now it's a wedge. Great. That means it's going to match up. What about the rest of them? This is where it gets kind of weird, okay? So here's my OH, it's gonna go down. My CH2, CH3 is gonna go back. And then by default, my H is gonna be planar. Same thing for the other side to look at where everything goes. So my H is up here. When I turn it to go down, now it's going to be planar because I'm turning it. At first it was like this and I'm turning it down one. So now it's going to be planar. And I know that my double carbon bond group is going to do something similar, but not exactly, because right now it's right here. When I turn, it's going to be out at me. And by default, the methyl group is going to be out here like this. So now we reevaluate again, love it. And we see, okay, well, these match up. So that's good, that means they're on the right track. But wait, CH3 matches up, but these two don't match up at this point. Ding, 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 ding. You know that you have stereoisomers because no matter how hard I try to make these match, squeaky, they won't match because one of them is matching and the other two aren't matching, which means that you have stereoisomers. Boom. Also, you know that this is a diastereomer because one of the carbons, the orientations are matching, and the other one, they're not. If both of them weren't matching, then you would have enantiomers, because enantiomers happen when both of them are different, and diastereomers happens when one of them is different. However, sometimes you turn stuff weird, your brain's not doing well in the quiz or the test, and you freak out, you don't have this either, so you're kind of like, shit, I've got to find a way to check. Wait, we can check. We're going to prioritize our carbons, and I'm going to do it the slow way first and then the fast way next. So you can draw a little box for your carbon, figure out how to prioritize it. We got an oxygen over here. We have this carbon right here. We have our ethyl group over here, and then we have our hydrogen over here. Doesn't matter which way you put them in, you're going to get the same answer regardless, but I'm just going to put them like this because I said so. We know that oxygen is the biggest, hydrogen is the smallest, easy. But what about these two? Whenever you have a double bond, you have to draw two of them. So that's why this is this carbon. These two carbons is the same carbon, but there's two bonds. This carbon has another carbon attached to it, but this one wins because it's heavier. This is looking scary. Go back to my other video. And now we do our little swirly thing. Instead of using a little molecule and trying to manipulate it and do its little thing, you can switch the hydrogen if it's not ready on the dash to make it a dash. So this hydrogen needs to be a dash. However, it's not. So we can switch these two, pretend that this is the 4 and that this is the 3, because now the 4 is on a dash, right? And then we do our thing. So right now, it looks like it's going clockwise, right? Look, as it's going clockwise. However, since we switch these two, we need to switch the orientation that we get. So right now it looks like it's an R because R is clockwise, but that means that it's actually an S. We have to do this 3 more times, right? So it's just gonna get easier, okay? So now we're gonna do this one. We've got our 1 carbon's gonna be this one because it's got all the stuff on it. We like the oxygen. And then it's gonna be this one, and this one, and this one. Similarly, we need to switch these two because this needs to be in the back. We're gonna put a 4 here and a 3 here. Right now, it looks like it's going clockwise again, which means that it's actually an S. We do the exact same thing. My foot is asleep. Oh my goodness. Sorry. We're gonna do the exact same thing for these 2 carbons. So this is gonna be a 1, this is gonna be a 2, 3, 4. Same exact thing. We're going to switch these. 3, 4. Right now it looks like it's going counterclockwise, but that means that it's actually going clockwise. So it's gonna be an R. And this one, we already know, stop, breaking point, content check. We know that, wait, these carbons looked the same, right? The OH is in the right place, this is in the right place, this is in the right place. Why are they different? Because it depends on how you look at the molecule. And we know that this one didn't match geometrically, but this one didn't match orientation-wise, if that makes sense. I don't know if I'm wording it right, But we know that we have diastereomers because of that. So if these are different, boom, this has to be an S, period. But we need to check our work. It would be silly not to because we've gotten this far. So we're gonna do the exact same thing. 1, 2, 3, 4. Switch these. 4, 3. Looks like it's R. However, it means it's an S. Now we see that we have these two are different. These two are the same. And that means that we have diastereomers. And that's the answer to number 2. Number 3 was a concept problem. So it's basically a vocab problem, so I'm not going to go over number 3. And number 4 is kind of exciting because it shows you an energy diagram and asks you what doesn't show what's on the energy diagram. And this question could have been a lot simpler, but it combined a bunch of topics into one. So we're going to go over what the energy diagram means and then also to solve the problem itself. So if we have something that looks like this, he's asking about this point. And we know that carbocations require a lot of energy. They're incredibly unstable, so they have a lot of energy. These parts of the reaction, they're just chilling. They're just like doing a little reaction thing. But this carbocation requires a lot of energy, so we know that this is the carbocation part of the reaction. And the answers, you can't see my computer screen, but the answers all show carbocations. So that means that what we're looking for is which carbocation is correct. 1, needs to be correct. 2, it looks like the answers are showing, okay, well, it looks like the carbocations all look the same, but they're different based on if they're represented as being planar, wedge, dash. Concept. Whenever we have a carbocation, it doesn't matter if it's secondary, tertiary. If I got something like this is just figurative. I'm literally drawing this out of my butt. Let's say that this was our carbocation. We want carbocations to be represented as planar no matter what, because that's how this should be represented. Technically, something that's trigonal planar doesn't need to have a wedge or a dash because there's only 3 of them. I can hold up 3 fingers like this and none of them is coming towards you or at you. I can do it like this, I can do it like this, which we'll see in a second, but this needs to be represented as planar, period. So up and down, straight up and down, you can tell that this is planar. And when it changes is when, if instead of looking at it like this, I looked at it like this. And that is what the question answers are asking you. So first we're going to do the mechanism up until the carbocation just for practice, and then we're going to go over which one is actually correct. So here is our problem. We have H3C and we have OH added to HCl, and it gives you the answer, so you don't have to worry about it. But anyways, we're going to take one of the lone pairs, skip to the hydrogen, break the bonds, blah blah blah. This is now 1, 2. Break this. I'm gonna put it down here, and now this, watch, planar because there's only 3 of them. And it's a carbocation. Normally put the carbocation down here, but it just helps my brain to keep it in the same spot as where the oxygen was. So now, this is our carbocation. Wait. Stopping. LOL. That's what we need to be looking at right now. So out of the answer choices, I'm going to erase this and leave this because that's what we're basing off of our work on. And we're given this, and I'm not going to draw the substituents because we already know 100% this is planar because it's literally just like this. So that one's good. What about this one? This is what I'm talking about, how instead of looking at a molecule like this, we're looking at it like this. So technically, I have one coming at me, one coming away from me, and one being planar. And I know that I can't bend my hand like that, ew, but that's this idea, is that if I turn a molecule from being flat like this to being sideways like this, then that means that one of them is going to be in the plane, because it's in the plane, looking at it. One of them is going to be away from me, this one. And one of them is going to be at me, like this. So this is representing a planar molecule. Okay, it's kind of weird. So we know that that one's correct. What about this one? What if we change the substituents? If this was A, B, C, and then we changed it to be like, I don't know, B, C, A, it's still the same thing, because it's like if we're doing this, it's harmless. We're just twisting the molecule. It's absolutely the same thing. However, you know that those are good. If we have something like this, you can tell I saved the wrong answer for last. This is not representing a planar molecule because there's a dash, period. That's the answer. This does not represent a planar carbocation because this is a dash. It should look like this because this is planar because there's no wedges or dashes. That's just like what it is. It is what it is. So those are the quiz questions, and I hope that this video was helpful.